we will continue initially with a review of monatomic statistical mechanics of monatomic gas, and then we will do diatomic gas today itself. We did it once before, but we need to redo many other aspects because these are fairly detailed things. You can call it as a revision, but it is more likely many new information will come in today's. And so, in the study of statistical mechanics and study of any subject which is a bit mathematical and involving a lot of equations, it is worth going through this many times. Like when you used to derive equations when you were a student, one of the things that we are told and we did is that we derive the same thing many times. That is the way to, you do not memorize it, but you derive it many times. You go through it many times. It is like painting. When you, in order to understand something and get it inside you deeply, you do like we do painting of the wall. You do several coats. So, we will briefly and quickly go through few things, and then we will go to the new things. Today we will, in a monatomic gas, we will do two new things which we missed before. Then we go to diatomic gases and we will do some old and some new. Now, we say that in the last class we discussed first the partition function, and the partition function is the thing that I have here on my board, the Qn, and in the circle rate, that Qn coming from integration over the momentum, and A integration gives volume, real space integration gives volume, and then this is essentially then what happened that Q, small q that we derived has contained this quantity and multiplied by the volume. So, n particles we have now q to the power n, and then we went and we derived that the free energy. So, all these details were done in the previous page. So, we did that we wrote down Qn is q to the power n by n factorial, and then we have the volume Qn to the power n factorial, and q is this quantity that 2 pi m kBT by h square to the power 3 by 2 and the volume V. That was the quantity. When that Qn with this q is used in the statistical mechanical expression of free energy, statistical expression of free energy in minus kBT ln Qn partition canonical partition function, then we get this. And then one get an expression of free energy in terms of n, total number of particles in the system, temperature of the system, and the volume of the system. This is really beautiful. An exact expression, a microscopic expression, what is Helmholtz free energy, and that is a function of A is a function of nVT, and I have those dependents, and we have now some very fundamental quantities like I have Boltzmann constant Kb, I have mass of the particle, and I have the Planck's constant. Okay, this is a beautiful, really beautiful expression, this in the box. Now, then I can calculate by using thermodynamic relation from this free energy. I can now calculate pressure. And then another beautiful thing comes in, that is equal to n kBT, which you all know, the ideal gas law. So, then the next what we did, we went on using that partition function and the Helmholtz free energy, we get the entropy, and the entropy then is obtained by dA dt V, the thermodynamic relation, and now we get a beautiful expression for entropy. Again, the expression of entropy includes the n, the number of particles, temperature T, and when I remove V by n by using the ideal gas law, then it is in pressure. So, entropy suddenly is a exact expression of which depends on total number of particles in the system, the pressure of the gas, and the temperature T. Again, I have the mass of the particles, is a monatomic gas, only one gas. This can be generalized to binary mixture or 3 particles things almost trivially. Then what will happen? I have to add, say I have argon and krypton, then I have n argon here, number of argon will come in here, and then mass of argon will come here, everything same, pressure remains the same. Then I will say n of the krypton, and then again mass of the krypton again remains the same. So, it's ideal gas law follows Raoult's law. So, you add up the entropy multiplied by the number of them, and if I say entropy per particle, then it becomes mole fraction. So, the things to remember, the things to really note, that we have a number of particles n, and we have the temperature T here, and we have the pressure P here. If you have the volume, there volume B. This is the famous Sackur-Tetrode equation, which I discussed, is used in many applications. But before I go, I really want to impress upon you the beauty of this equation, that this is where the temperature comes as 3/2. So, if I combine temperature with this, it becomes T to the power 5/2, and these are much less known than and much less emphasized, but these are the elegance, but these are beautiful thing. So, then we commented that we use this Sackur-Tetrode equation in a drug DNA intercalation. We discussed this thing that this a drug is going to go into minor or major group, and this is a very important problem in chemotherapy or many other drugs. And then in doing the calculation, there is a beautiful paper by Charles, then there is a beautiful paper on drug DNA intercalation, which you can do the name of Casey Hines, J.T. Hines, Jacks, I think 2000, probably 13 or so. And with that, this thing was used, the Sackur-Tetrode equation was used to calculate the free energy of intercalation. And this is very important that we get the free energy of intercalation, because that allows us to choose or select drugs. Very important. Then we use it extensively in the formation of water droplets in the cloud. And that this entropy, when the water goes to form a droplet, a water droplet, which has to become rain, that is lot of loss of entropy, because they instead of moving separately, they are stuck together and a big mass, and so then the entropy decreases. But that thing is in used in many other, in nucleation, many other things. So, continuing now, that I gave some numbers, because you should always think in terms of numbers, and in entropy, number is always in terms of this kb unit, that is called entropy unit, in honor of Boltzmann constant. Now, this is under ambient conditions, that means their respective their liquid state, their gas state. Neon is the entropy is this, and argon is this. So, they are pretty close to each other, this entropy, and they are with the whatever experimental values we have by integrating thermodynamic variables, they increase almost exactly with the experimental values. So, now we will do 2 simple calculations, which we have not done before, and they are very nice calculations. They are simple calculations, but they use some mathematics. So, we now derived expression for pressure, we derived an expression for entropy, we derived an expression for free energy, we derived an expression specific heat 3/2R and 5/2R. 3/2R comes just as I showed you from A, and then 5/2R because you add R to it, which comes from PV terms, H equal to E plus PV, because Cp is dA derivative of enthalpy, and enthalpy comes with a PV, extra PV terms. So, that PV, then we replace PV by RT, and you take the derivative, then one R comes which adds to 3/2R, and you get 5/2R. That is the reason that Cp is 5/2R, and Cv is 3 by 2 R, the PV term, the extra PV terms that goes over to becomes RT in the for a mole, 1 mole for ideal gas law. Now we will do something. We have discussed the grand partition function, but we have not used too much of grand partition function. We will use the grand partition function later quite a bit, but now we are just somewhere about in the beginning of the statistical mechanics course, and but we are already getting many nice results, but we will get one more nice results. The result that we used extensively in your freshman chemistry or in sophomore chemistry, and but in solution chemistry or in undergraduate chemistry, at least I can personally say myself, I found it boring, and even now teaching it sometimes fairly boring, though there are a lot of very nice books have come to make it easier. But the problem of those physical chemistry equations is that they are introduced much of the time, they are not derived, and example says a solvation, the concept of chemical potential. Why the chemical potential goes at logarithmic term, that comes as a kind of derivation, as a definition. But what we will do now, it is not a definition, we will derive it from statistical mechanics, more fundamental, why chemical potential goes at logarithmic of density. It is a very important quantity. Remember in your undergraduate study that we start working on a chemical potential, and which is a very important quantity, and in describing the flow of matter, but that is proportional to logarithmic density. So, if we keep low density, high density together, then matter flows from low density to high density, and the driving force will be given by the logarithmic of density, and that goes into the diffusion equation in Fick's law and all this kind of stuff, which we will do later as we go along the way in a little bit of time dependent statistical mechanics, which is just a wonderful subject. So, what we did before that, we did the grand partition function, and grand partition function is this quantity e to the variant, that is can be, I wrote it also like that. This quantity, and here the Z is the fugacity and mu is the chemical potential. So, Z equal to e to the power beta mu. So, this is the relation between chemical potential and fugacity, Z. Mu is the chemical potential and Z is the fugacity. So, this is the, and remember that this Z or beta mu comes, these in terms was a Lagrangian multiplier or Lagrange undetermined coefficient, and mu came as the conservation condition, that number of particles must be conserved. So, we form from microcanonical ensemble to when you go into canonical ensemble, we introduced conservation of energy of my super system, and that conservation of energy in the super system, that means there is energy exchange between the systems, but in the super system which has been put by contact, putting them in contact with each other so that exchange energy and can attain a temperature T. Then however, the conservation of the total thing was maintained, conservation of total energy of my super system, and that conservation condition gave rise to beta, the temperature beta, the temperature term beta. Beta is 1 over kBT. It came as an undetermined coefficient, but it came as a conservation condition. Similarly, when you go to grand canonical partition function, then the chemical potential or fugacity came again as an undetermined coefficient, but to take care of the conservation of the number of particles. So, this is very important, that they come very naturally from a very fundamental condition, that is conservation of energy, conservation of number of particles. That means they are not ad hoc. Now, then with that going that the way, just like Qn was sum over energy levels e to the power minus eta I kBT, we get grand partition function as e to the power beta mu n and Q n Vt, which is written here in another form. So, now we will do something very interesting with that. Before we do that, if I now talk of ideal gas, in ideal gas I know Q now. Q is a quantity which goes as Q to the power n by n factorial. This is the ideal gas or monatomic gas. That means I have an exact expression for Q. Now, those of you who like mathematics, you can immediately see that this is at something to the power n, and this is also something to the power n. Z is e to the power minus beta u. So, this is z to the power n, this quantity is z to the. So, I have one to the power n and the z. So, z and q multiply and to the power n and divide by n factorial, and what does that remind you? That remind you that becomes nothing but an exponential function. So, e to the power zq, it becomes e to the power zq. So, now and that, so now we know so I have an expression for grand partition function, that is e to the power zq, and I know q. So, this is my grand partition function, beautiful. So, now I also know that chemical potential and number of particles are conjugate of each other, and the exact relation between them is just like pressure is dV dP, entropy is ds dt, dA dt, and everything like that. Number is related to this grand partition function through A of chemical potential. Now, when I put Q and all these things together here, because this is e to the power beta, Z is again e to the power beta mu, I add them here, put them, I take a log term, and then this beta mu comes in front, and then ln v will comes it, and then I take the derivative of this quantity, then e to the power zq, then it becomes it comes out as zq, and q is proportional to volume, and z is e to the power beta mu. Then when I do that simple algebra, I get the derivative, derivative of exponential is exponential, brings me beta down, and when I do these things together, I get just this beautiful relation. So, now you see the volume V, the volume if n becomes this quantity. So, now I can take this V on that side, or I can take, I can take V on that side, I can take n by V, that becomes density and lambda q. So, this whole part is taken there, so giving rise to me this term, and is e to the power beta mu, and then I take logarithmic term, and beta becomes 1 over kBt. So, you can easily see that I get this beautiful relation, I like, so I use one more color. So, this beautiful relation. Now, that means chemical potential is logarithmic of density. Many times we write ln rho, which is not correct, because you cannot put a dimensional quantity within logarithmic, or you cannot put dimensional quantity in exponential. So, something is missing in these equations we do, but in classical physical chemistry, we just write ln rho, we cannot not, there is always that function lambda cube there. And or many times what we do chemical potential with respect to another species or another state, then delta mu term, then I have ln minus ln, and then that becomes ln A minus ln B is ln A by B, and then lambda cube cuts out, you get ln rho 1 by ln rho 2, ln rho 1 by rho 2, sorry. So, that is why lambda q is always kind of a silent player in all these things, but I really want to impress upon you this beautiful relation that mu goes as ln rho. This is something which is hugely used. So, when I talk of non-ideality, so this ideality, chemical potential is dependent on linear logarithmic dependence on density. But when I talk of non-ideality now, the non-ideality we just introduced other activity coefficients and other quantities. That is where, this is where it enters all these things. So, there is a very solid foundation of these things. These terms were actually done by Gibbs himself. So, that is why in the thermodynamics of solution theory, many things that gives equation, gives Duhem equation and all those stuff, because this was worked out by Willard Gibbs himself. Now, so there is a little bit of writing here now that let me read through. Chemical potential is the change in internal energy on addition of an extra particle when the entropy, and that is given here, these things. However, an extra particle would result in more number of arrangements in the same volume. As a result, entropy increases. So, basically what one trying to tell here, the chemical potential in and that is how it is done in undergraduate textbooks. The chemical potential in ideal gas when their molecules are not interacting with each other is an entropic origin. It is very important to understand that chemical potential in ideal gas law is an entropic origin. So, ideal gas law gives us a fantastic way to talk of entropy, because all you have is entropy. And what we do then later when you add interactions, many times we try to preserve the entropic term, the ln rho term, like in, remember, binary mixture, ideal entropy of mixing. What is that? That xi ln xi. So, essentially rho I ln rho I, which has the same basically the same structure of ln rho term coming and then multiplied by the relative weight of that ln rho term. This is just beautiful things that the way they fit together. But this is a very important thing is taught here, that it is the entropy that is the important player here, because in ideal gas law we do not have interaction energy, but by entropy alone we get a huge number of phenomena. And as again I am repeated, this part of entropy we try to take over when you do interacting systems, the real systems. These are not real, but very important, just like particle in a box in quantum mechanics is important, harmonic oscillator is important, rigid rotator is important, and then you go and start doing, after doing these things you start doing hydrogen atom and hydrogen molecules. Here also we will go over to the complex systems. Okay. So, now we now know we want to go to the and very important second calculation of the monatomic gas, ideal monatomic gas. Then we and a result of far reaching consequence, a result that is used extensively in for example solid state physics and in spectroscopy, in conductivity of solids, the electron gas and that kind of a problem, where we need to know what is the number of density of states, how many number of quantum states between energy E, at energy E between E and dE, that is called density of states, and is very important how the density of states changes with energy. And there is a simple trivial calculation, but very nice calculation, that let us go through that. Now, you have done you have done quantum mechanics, particle in a box, and you know that the energy is given by this quantity, that E is a square by 8 ml square, in x square, in x and y are the quantum numbers, and their values are from 1, 2, 3, 4, like that. These are the we have discussed at length why this quantum number starts from 1 and they are integer numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Now, this is a beautiful equation. Now, I realize if I can little bit messaging of that, then nx square, ny square, nz square, I can write it at n square. Then that n square, and I can take now this quantity on this side, then I can write, and this is going to be very important, 8 ml square by 8 square. I go there. So, and then n square becomes equal to 8 ml square by 8 square E term. Now, this is I can call these as nx square, n square, all these things like x square plus y square plus z square equal to a square. That is the equation of sphere. So, this is the equation of sphere, and then I will have something very interesting thing to do, because this centered at origin in 3 dimension. Now that becomes the radius now, but I know the radius, that radius in turn is given by that. Okay. Now one plays a very smart game, and is that we now want to consider that we have a sphere, hypersphere, let me consider to like that, and now this is a sphere. Now in that sphere I have nx, ny, nz all has to be in the positive. I do not have nx, ny, nz negative. So if I say ny, nz and nx, now I want to calculate. Now I say they are all, I point, and then these are the point which are correspond to nx, ny, nz in that one one part, one octant of that in this sphere, 3-dimensional sphere. So now I can now play the smart game. I said, okay, the total number of states would be, these are very large. In order to calculate the total number of states, all I need to do, since they are placed unit 1, and this is the real crux of the matter, that nx, ny and nz increases by 1. Nx goes 1, 2, 3, 4, ny goes 1, 2, 3, 4. So there is this grid that I am forming, I have all spacing 1. So that allows me to, if I get the volume, because of them this unit thing, the volume gets me total number of density, total number of states, and that is what I do now. And since 1/8 of it, so I know the total number, total volume, and total volume is this 4 pi by 3 n cube. N is the radius, and n is nx square plus ny square plus nz square, and then I have this total number in all these region, all the 1/8 is 1/8 pi by 3 n cube. That is just beautiful. So now I also know what is n. I just did in the last class. So by n is n square. N square is 8 ml square by h square. That I did in the last slide. So n cube is then 8 ml square h square by 3 by 2. This is just wonderful. So total number of states increases as e to the power 3 by 2. So it increases fairly rapidly, and also what is very interesting, that it depends not only on the energy, it also depends on the mass, and it depends on the length of the box. Remember, L is the length of the box in this particle in a box model. So now, but this is not the density of states. I am interested in density of states. It is not the density of states. This is the total number of states. Now, how do you do density? What is the definition of density of states? Density of states is that you take the energy, the number of states with E and E plus D. That is the density of states. And so you do it by taking derivative. This number. So it's increase from E to E plus del E. It of course will be proportional to del E in a linear thing. So now we do that little thing, and this we get that density of this is omega is the density of states, fairly universal notation, and then I get the derivative in del E. I can divide by del E, and this del E is lurking here. When I do that, then 3 by 2 comes out, and this 3 by 2 comes here, and that 3 cancels this, and I get a 2, and 2 is here, so I get 4. So I get pi by 4 here, then 8 ml square by square remain untouched 3 by 2, and 3 by 2 become root e, e to the power 3 by 2 derivative e to the power half root e. So this is a beautiful result, which shows that omega e goes as square root e. Density of states in a particle in a box goes, and this is very important. This is the result, as I told you, the result is used in many applications. Now there is one more interesting result, very interesting result that comes. Now we do not have one particle, we have n number of particles. So, we do not have a sphere, we have a hypersphere, and in a hypersphere now you have the volume that is going as 3 to the power n by 2, and then you can do exactly same derivative. I say 3 n by 2 becomes minus 1, and these in the volume this gamma to the power 3 n by 2, and this is gamma n plus 1 is nothing but our n factorial, and this comes in the volume of the 4 pi by 3, that factor comes like that, and then this is coming again from the particle in a box energy. So, you now have density of states of n particle systems. So, this is the density of states of n particles in a cube of length L. So, you have a cube in a hyper of length L, and this beautiful thing now is omega E del E. You can, it has to be proportional del E, but del E is not the important quantity. Important quantity is these two n factorial that comes from the same logic as partition function, but this is the one which comes from the factors that come in the volume and e to the power 3n. So, now you can see a very important thing that we made already allude to in the statistical mechanics in the initial part, that there is a huge number of states when you, particularly when you go to little high temperature. So, number of states or density of states of n particle system scales as e to the power n, and that is a very important result, and this means there are a huge number of states up there, and this is an exact result in an ideal gas law, exact result, but as I am again and again telling, much of it goes over even in interacting system, and this is the one which is used now in the conductivity problem and many other calculations of solid state physics, where electrons are used as free particles, and that is a very important model of solid state physics, that free electron gas. And when you want to talk of free electron gas, we take the mass of electron m there, and then we calculate this, we use these things in the particle okay. So, this is what we wanted to talk of, this beautiful thing of in a way of classical and quantum, the beautiful interaction between quantum and statistical mechanics, and then so we will take a short break, and we will start on the diatomic